In the depths of space, where silence reigns absolute and distances stretch beyond human comprehension, there burn countless points of light. These are the stars, cosmic furnaces suspended in the void, each one a massive sphere of plasma held together by its own gravity, generating energy through nuclear fusion at its core. They are not merely distant suns scattered randomly across the heavens, but fundamental components of the universe itself, the engines that transform simple hydrogen into the complex elements that make up planets, life, and everything we know. To understand stars is to understand the very fabric of cosmic existence, to glimpse the processes that have been unfolding for billions of years, creating and destroying, birthing and ending in an eternal cycle that continues even now. A star begins as nothing more than a concentration of gas and dust, a slight overdensity in the vast molecular clouds that drift through galaxies. Gravity, patient and inexorable, pulls this material together over millions of years, compressing it, heating it, until eventually the pressures and temperatures at the center become so extreme that hydrogen atoms are forced to fuse into helium, releasing tremendous amounts of energy in the process. This is the moment of ignition, when a star truly begins its life, when the inward pull of gravity is balanced by the outward pressure of radiation from the fusion reactions at its core. This delicate equilibrium can last for millions, billions, even trillions of years, depending on the star's mass, creating a stable period during which the star shines steadily into the cosmos. The light that reaches us from these distant stars has traveled across unimaginable expanses, journeying for years, centuries, sometimes millennia before finally entering our telescopes and our eyes. Each photon carries with it information about the star that produced it, encoded in wavelengths and spectral lines that revealed the star's temperature, composition, motion, and age. When we look at the night sky, we are not seeing the universe as it is now, but as it was, a tapestry of different moments in cosmic history, all arriving at our present simultaneously. The nearest stars show us the recent past, just a few years ago, while the most distant visible objects reveal the universe as it existed when our planet was still young, or even before Earth had formed at all. Stars come in a tremendous variety of sizes, temperatures, and colors. The smallest red dwarfs contain just a fraction of our sun's mass, burning so slowly and efficiently that they can continue their fusion reactions for trillions of years, far longer than the current age of the universe. The largest blue supergiants contain dozens or even hundreds of solar masses, burning with such ferocity that they exhaust their nuclear fuel in just a few million years, living fast and dying young in catastrophic explosions. Between these extremes lies a continuous spectrum of stellar types, each with its own characteristics, its own life cycle, its own destiny written in the laws of physics that govern their behavior. The surface temperature of a star determines its color. The coolest stars glow red, their surfaces barely reaching 3,000 degrees Celsius, while the hottest blaze blue-white at temperatures exceeding 30 or 40,000 degrees. Our own sun, a yellow dwarf star, sits comfortably in the middle of this range with a surface temperature of about 5,500 degrees Celsius. This temperature is not arbitrary, but is directly related to the rate of fusion reactions in the core and the efficiency with which energy is transported from the center to the surface. The interplay between gravity, pressure, temperature, and the properties of matter in different states creates the precise conditions that define each star's appearance and behavior. Inside every star, energy moves outward from the core through two primary mechanisms. In the innermost regions, where matter is dense and opaque, energy travels through radiation as photons are absorbed and re-emitted countless times, each interaction redirecting them slightly until they gradually work their way toward the surface. This journey can take hundreds of thousands of years for a single photon, bouncing randomly through the dense stellar interior in a process called a random walk. Further out, in regions where the temperature difference between layers creates instability, convection takes over, with hot plasma rising toward the surface while cooler material sinks back down, creating circulating currents similar to boiling water, but on a cosmic scale. These convection zones can be seen on the Sun's surface as the granular pattern that covers its photosphere, each granule a convection cell the size of a continent, constantly churning and renewing itself every few minutes. The energy produced by a star's fusion reactions is truly staggering. Our Sun converts approximately 4 million tons of matter into pure energy every single second, following Einstein's famous equation relating mass and energy. This energy radiates outward in all directions, warming planets, driving stellar winds, and illuminating the surrounding space. Yet despite this prodigious output, the Sun will continue burning for another 5 billion years before exhausting the hydrogen in its core, a testament to both the vast reserves of fuel available and the efficiency of stellar fusion. Even more remarkably, larger stars burn through their fuel millions of times faster, yet contain only dozens of times more material, demonstrating how dramatically the fusion rate scales with mass. Stars are not solitary objects, but exist within vast communities. Most stars form in clusters, born together from the same molecular cloud, beginning their lives as siblings sharing a common origin. Over time, gravitational interactions and galactic tides disperse these clusters, sending their members off on independent paths through the galaxy. But for millions or even billions of years, these stellar families remain bound together, evolving in parallel. Some clusters, called open clusters, contain hundreds or thousands of relatively young stars loosely associated in regions of recent star formation. Others, the globular clusters, are ancient dense spheres containing hundreds of thousands or even millions of old stars, orbiting in the halos of galaxies, survivors from the early epochs of galactic formation. The nearest star to Earth, beyond our own Sun, is Proxima Centauri, a small red dwarf lying approximately 4.2 light-years away. This means that light, traveling at 300,000 kilometers per second, takes more than 4 years to cross the distance between that star and our solar system. On human scales, this distance is incomprehensible. The fastest spacecraft ever built would require tens of thousands of years to reach even this closest stellar neighbor. Yet, in galactic terms, Proxima Centauri is practically next door, so close that it and its companion stars Alpha Centauri A and B form a multiple star system that appears to the naked eye as a single point of light in the southern skies. Many stars exist in binary or multiple systems, gravitationally bound to one or more companions, orbiting their common center of mass in a cosmic dance that can last billions of years. These systems offer unique insights into stellar evolution, as the stars influence each other's development, sometimes transferring mass back and forth, sometimes merging catastrophically, sometimes simply aging together in parallel. Close binary systems can create exotic phenomena, such as when a compact stellar remnant like a white dwarf or neutron star pulls material from a larger companion, creating accretion disks and nova explosions. In wider binaries, the stars may barely interact at all, each following its own evolutionary path while remaining gravitationally linked across distances of hundreds or thousands of astronomical units. The study of stars has revealed fundamental truths about the universe. By analyzing stellar spectra, astronomers can determine not only the temperature and composition of distant stars, but also their motion toward or away from us through the Doppler shift of spectral lines. This technique has revealed that the universe is expanding, that galaxies are moving apart from one another, and that the cosmos had a beginning in an incredibly hot, dense state, approximately 13.8 billion years ago. Stars serve as cosmic laboratories where extreme conditions exist that cannot be replicated on Earth, allowing scientists to test physical theories under circumstances of enormous pressure, temperature, and density. The behavior of matter inside stars, where electrons are stripped from atoms and nuclei are forced together by tremendous gravitational compression, continues to challenge and refine our understanding of quantum mechanics, nuclear physics, and general relativity. Chapter 2. Birth in stellar nurseries. The creation of stars begins in the cold, dark molecular clouds that drift through galaxies, vast accumulations of gas and dust spanning hundreds of light years, containing enough material to form thousands or even millions of stars. These clouds, composed primarily of hydrogen and helium left over from the Big Bang, along with trace amounts of heavier elements forged in previous generations of stars, maintain temperatures just a few degrees above absolute zero, cold enough that atoms can combine into simple molecules like hydrogen gas, carbon monoxide, and various organic compounds. The density of these clouds is extraordinarily low by terrestrial standards, containing perhaps just a few hundred atoms per cubic centimeter, yet because of their immense size, they accumulate tremendous total mass, sometimes equivalent to millions of suns. Within these molecular clouds, there exist regions of slightly higher density, places where random fluctuations or external disturbances have compressed the gas more than average. These overdense regions exert a stronger gravitational pull on the surrounding material, slowly attracting more gas and dust toward themselves. As more material accumulates, the gravitational attraction increases, pulling even more matter inward in a self-reinforcing process. This is the beginning of gravitational collapse, the fundamental mechanism by which stars form, driven entirely by one of nature's most basic forces. The collapse proceeds slowly at first, taking millions of years for the cloud to contract noticeably. But as the density increases, the gravitational forces strengthen and the process accelerates. Not all molecular clouds spontaneously collapse to form stars. Many remain stable for long periods, their internal gas pressure and turbulent motions providing enough support to resist gravitational compression. Something must trigger the collapse, some event or disturbance that tips the balance in favor of gravity. Often this trigger comes from external sources. The shock wave from a nearby supernova explosion can sweep through a molecular cloud, compressing the gas and initiating collapse in multiple locations simultaneously. The formation of massive stars can trigger further star formation in surrounding regions as their intense radiation and stellar winds compress nearby gas. Even the gravitational influence of spiral density waves passing through a galaxy's disk can compress molecular clouds enough to begin the collapse process, creating the spiral arms where most star formation occurs in disk galaxies. As a region of the cloud begins to collapse under its own gravity, it fragments into smaller clumps, each one destined to become an individual star or stellar system. This fragmentation occurs because the cloud is not uniform, but contains density variations, temperature differences, and turbulent motions that create instabilities. The largest clumps will form the most massive stars, while smaller concentrations produce lower mass stars and brown dwarfs. The process of fragmentation can continue down to smaller and smaller scales, creating a hierarchy of structures within the collapsing cloud, which explains why stars typically form in clusters and associations rather than in isolation. A single molecular cloud can give birth to hundreds or thousands of stars in a relatively brief period of cosmic time, transforming a cold, dark nebula into a brilliant stellar nursery. As each collapsing fragment contracts, gravitational potential energy is converted into thermal energy, causing the temperature at the center to rise. Initially, this heat can radiate away into space, but as the fragment becomes denser and more opaque, the thermal energy becomes trapped, causing the central temperature to increase more rapidly. After perhaps 100,000 years of collapse, the central region becomes hot and dense enough to be considered a protostar, an object that will eventually become a star but has not yet begun nuclear fusion. The protostar continues to grow as more material from the surrounding envelope falls onto it, adding to its mass and further compressing its core. During this phase, the protostar is surrounded by a rotating disk of gas and dust, material that has too much angular momentum to fall directly onto the star and instead settles into an orbiting structure that will later form planets, asteroids, and comets. The protostellar phase is a time of intense activity and dramatic changes. The infalling material releases gravitational energy as it strikes the protostar's surface, heating the young object and causing it to shine brightly in infrared wavelengths, even though nuclear fusion has not yet begun. Jets of material stream out along the protostar's rotational axis, perpendicular to the accretion disk, carrying away excess angular momentum and clearing out the regions above and below the disk. These protostellar jets can extend for light years, plowing into the surrounding molecular cloud and creating shock waves that heat the gas, producing the beautiful Herbig-Haro objects observed by telescopes, glowing knots and filaments that mark the violence of stellar birth. The disk itself is far from placid, with material spiraling inward toward the protostar, heating through friction and magnetic interactions, occasionally producing flares and outbursts that temporarily brighten the young object. For a low-mass protostar destined to become a star similar to our Sun, the journey from initial collapse to main sequence can take 10 to 50 million years. A brief moment in cosmic time, but still far longer than human civilization has existed. During this period, the protostar slowly contracts and heats, following what is known as the Hayashi track on the Hertzsprung-Russell diagram, a graph that plots stellar luminosity against temperature. The protostar begins as a large, cool object, but as it contracts, its surface temperature increases while its luminosity decreases, since the smaller radius more than compensates for the higher temperature. Eventually, when the central temperature reaches approximately 10 million degrees Celsius, hydrogen nuclei begin to fuse into helium, and the star reaches the main sequence, the long, stable phase where it will spend most of its life. Massive protostars follow a different path. Because they accumulate material much more rapidly and compress more dramatically under their own intense gravity, they heat up and begin hydrogen fusion while still accreting matter from their surrounding envelope. This creates a complex situation where the star is simultaneously growing through accretion and burning hydrogen in its core, surrounded by a cocoon of gas and dust that obscures it from optical observation. The radiation pressure from the young massive star is enormous, pushing against the infalling material and eventually halting further accretion once the star reaches a certain mass. This feedback mechanism helps explain why there appears to be an upper limit to stellar mass, around 150 to 200 solar masses, beyond which stars cannot grow because their radiation pressure prevents any additional matter from falling onto them. The environment of a stellar nursery is incredibly hostile. The intense ultraviolet radiation from hot young stars ionizes the surrounding gas, creating glowing nebulae that can be observed across the galaxy. The stellar winds from massive stars carry away tremendous amounts of material, sweeping clear cavities in the molecular cloud. When the most massive stars reach the end of their brief lives, they explode as supernovae, blasting shock waves through the cloud that can compress remaining gas and trigger new generations of star formation, while simultaneously dispersing and destroying parts of the cloud. This process of star formation is inherently self-limiting. The stars that form from a molecular cloud will eventually disrupt and destroy the very cloud that created them, ending the star formation episode and leaving behind a cluster of young stars embedded in the expanding remnants of their natal nebula. Throughout our galaxy and others, stellar nurseries are ongoing, creating new stars even now, billions of years after the first stars formed. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one of the nearest stellar nurseries, lying about 1,300 light-years away. Within its glowing clouds, telescopes have revealed thousands of young stars in various stages of formation, from dense molecular cores just beginning to collapse to bright young stars that have already cleared away their surrounding material. The pillars of the Eagle Nebula, captured in one of the Hubble Space Telescope's most famous images, show towering columns of gas and dust being eroded by radiation from nearby young stars, with new protostars forming in dense knots at their tips, shielded from the destructive radiation by the columns themselves. These regions offer invaluable insights into the star formation process, allowing astronomers to observe many different stages of stellar birth occurring simultaneously. Chapter 3. Protostars and the path to ignition. The protostellar phase represents a critical transition, the period when a collapsing cloud fragment transforms into an actual star capable of nuclear fusion. During this phase, which can last from tens of thousands to millions of years depending on the star's final mass, the protostar exists in a state between formation and maturity, growing through accretion while gradually heating toward the temperatures necessary for fusion. The physics governing this phase involves complex interactions between gravity, thermodynamics, magnetic fields, rotation, and radiative processes, all working together to shape the emerging star. Understanding protostars requires examining not just the central object, but the entire system of disk, envelope, and outflow that characterizes young stellar objects. A protostar's evolution is fundamentally a story of energy balance. As material falls onto the protostar, gravitational potential energy is released, converted into kinetic energy and then into heat as the infalling matter crashes into the surface or accretes through the disk. This energy must go somewhere. Initially, it radiates away relatively easily, cooling the protostar and allowing further collapse. However, as the protostar becomes denser and more opaque, thermal energy becomes trapped and the interior temperature begins to rise significantly. The increasing temperature creates pressure that opposes further collapse, slowing but not stopping the contraction. The protostar enters a phase of quasi-hydrostatic equilibrium, where gravity and pressure nearly balance, but a slight imbalance allows continued slow contraction and heating. This is the Kelvin-Helmholtz contraction phase, named after the scientists who first understood this mechanism in the 19th century. The central temperature of a contracting protostar increases steadily as gravitational energy is converted to heat. At around 1 million degrees Celsius, deuterium, a heavy isotope of hydrogen containing 1 proton and 1 neutron, begins to undergo fusion reactions with normal hydrogen. This deuterium burning produces a temporary surge in energy output, causing the protostar's contraction to slow or even briefly halt. However, deuterium is exceedingly rare, comprising only about 20 parts per million of typical interstellar material, so this phase is short-lived, lasting perhaps 10,000 years for a solar mass protostar. Once the deuterium is exhausted, contraction resumes, and the central temperature continues to climb. The protostar's surface during this phase is vastly different from that of a mature star. Covered by spots and bands created by magnetic field interactions, swept by powerful winds, and pelted by infalling material, the protostellar surface is chaotic and variable. The protostar's luminosity can fluctuate dramatically over timescales of days, months, or years as the accretion rate varies, sometimes increasing by factors of hundreds during episodes called few Orionis outbursts, named after the star where this phenomenon was first observed. These outbursts occur when instabilities in the accretion disk cause material to suddenly cascade inward, dramatically increasing the accretion rate onto the protostar and causing a corresponding surge in brightness that can last for decades or centuries before subsiding. The accretion disk surrounding a protostar is not merely a passive reservoir of material, but an active dynamic structure where matter spirals inward while angular momentum is transported outward through viscous friction and magnetic torques. The inner regions of the disk closest to the protostar can reach temperatures of thousands of degrees, hot enough to vaporize dust grains and ionize gas, creating a region where the disk's material exists as plasma. Further out, temperatures drop and various compounds condense from the vapor, creating the grains that will eventually coalesce into planets. The disk's structure changes with distance from the protostar, creating distinct zones where different materials can exist in solid form, from refractory compounds like calcium-aluminum inclusions close in, through silicate rocks and minerals at intermediate distances, to volatile ices of water, methane, and ammonia in the cold outer regions. Magnetic fields play crucial roles in protostellar evolution. The collapsing molecular cloud contains weak magnetic fields that become amplified as the material contracts, since the magnetic field lines are frozen into the conducting plasma. These fields can channel accretion flows, directing material from the disk onto the protostar along magnetic field lines that connect the disk to the stellar surface. The same fields help launch the powerful bipolar outflows and jets that characterize young stellar objects, though the exact mechanism remains an active area of research. The jets themselves are remarkable structures, carrying away angular momentum and energy from the star disk system, sometimes achieving velocities of hundreds of kilometers per second, as material is accelerated along the rotating magnetic field lines that thread through the disk and emerge along the rotational axis. As the protostar continues to contract and heat, it eventually reaches a critical threshold. When the central temperature climbs above 10 million degrees Celsius, protons, the nuclei of hydrogen atoms, begin to have sufficient kinetic energy to overcome their mutual electrostatic repulsion and approach close enough that the strong nuclear force can bind them together. This marks the onset of the proton-proton chain reaction, the primary fusion process in low and medium mass stars. Two protons fuse to form a deuteron, which quickly captures another proton to form helium-3, and then two helium-3 nuclei combine to form helium-4 while releasing two protons. The net result is that 4 hydrogen nuclei are converted into one helium nucleus, with a small fraction of the mass, about 0.7%, converted into energy according to Einstein's equation. This energy, emerging as gamma rays from the fusion reactions, provides the pressure needed to halt the gravitational contraction. The moment when fusion reactions become self-sustaining is the true birth of a star, the point at which the object transitions from protostar to main sequence star. For a star of the Sun's mass, this occurs after approximately 50 million years of collapse and contraction. More massive protostars reach fusion much more quickly, sometimes in less than 1 million years, because their stronger gravity compresses and heats the core more rapidly. Lower mass protostars take longer, sometimes more than 100 million years for the smallest stars. Brown dwarfs, objects with masses below about 8% of the Sun's mass, never achieve the temperatures necessary for sustained hydrogen fusion, remaining failed stars that shine dimly from the heat of their gravitational contraction and deuterium burning before slowly cooling over time. Once a star begins hydrogen fusion, it settles onto the main sequence, where it will remain for the vast majority of its life. The newly born star continues to clear away the remaining material from its formation, its radiation and stellar wind gradually dispersing the envelope of gas and dust that surrounded it. The accretion disk, no longer being replenished from the envelope, begins to dissipate as well, though this process can take millions of years. The disk material doesn't simply vanish, much of it is pushed outward by radiation pressure and stellar winds. Some falls onto the star, and some coalesces into planets and smaller bodies. After a few million years, the star emerges from its cocoon, now visible at optical wavelengths, surrounded perhaps by a young planetary system in the process of formation, or by a debris disk of leftover material, or simply by empty space if all the disk material has been consumed or expelled. The final mass of a star, determined by how much material it accretes during the protostellar phase, is the single most important property that will dictate its entire future evolution. This mass determines the core temperature and pressure, which in turn determines the rate of fusion reactions, which determines the luminosity, surface temperature, and lifetime. A star twice as massive as the Sun will be more than 10 times as luminous and will exhaust its hydrogen fuel in less than 2 billion years instead of 10 billion. A star half the Sun's mass will be less than 1/10 as luminous and will burn for hundreds of billions of years. This extreme mass dependence means that the most massive stars live fast and die young, while the least massive will outlive the current age of the universe many times over, continuing to shine long after galaxies have merged and evolved beyond recognition. Chapter 4. Main Sequence. Stars, the long equilibrium. The main sequence represents the longest and most stable phase of stellar existence, a period of equilibrium where the star burns hydrogen in its core and maintains a nearly constant size and luminosity. This phase is not a single moment, but a gradual progression spanning millions to trillions of years, during which the star slowly converts its hydrogen fuel into helium while barely changing its outward appearance. The main sequence is where stars spend approximately 90% of their active lives, making it the most common state for stars observed throughout the universe. When we look at the night sky, almost every star visible to the naked eye is currently on the main sequence, steadily fusing hydrogen in the same stable configuration that our Sun has maintained for the past 4.5 billion years, and will continue for another 5 billion. The fundamental principle governing main sequence stars is hydrostatic equilibrium, the precise balance between gravity trying to compress the star inward and pressure from hot gas and radiation trying to expand it outward. At every point within a main sequence star, the inward gravitational force on each layer is exactly balanced by the pressure difference between that layer and the one above it. This equilibrium is remarkably stable. If the star contracts slightly, the core becomes hotter and denser, fusion reactions accelerate, pressure increases, and the star expands back to its equilibrium size. If the star expands slightly, the core cools, fusion slows, pressure decreases, and gravity contracts the star back to equilibrium. This self-regulating mechanism, often called the stellar thermostat, ensures that main sequence stars maintain nearly constant conditions over immensely long timescales. The energy source powering main sequence stars is nuclear fusion in the core, where temperatures and pressures are extreme enough to force hydrogen nuclei together, despite their electrostatic repulsion. In stars with masses similar to or less than the Sun, the dominant fusion process is the proton-proton chain, a series of reactions that ultimately converts 4 hydrogen nuclei into 1 helium nucleus. The process begins when 2 protons collide with sufficient energy to fuse, forming a deuteron, a positron, and a neutrino. The deuteron quickly captures another proton to form helium-3, releasing a gamma ray. Finally, 2 helium-3 nuclei collide to form helium-4, releasing 2 protons that can begin the cycle again. Each complete cycle converts a tiny fraction of mass into energy, but with trillions upon trillions of reactions occurring every second, the total energy output is staggering. In more massive stars with core temperatures exceeding about 15 million degrees Celsius, a different fusion process dominates, the CNO cycle. This process uses carbon, nitrogen, and oxygen nuclei as catalysts that facilitate the fusion of hydrogen into helium. The cycle begins when a carbon-12 nucleus captures a proton, becoming nitrogen-13, which beta decays to carbon-13, which captures another proton to become nitrogen-14. The nitrogen-14 captures a proton to become oxygen-15, which beta decays to nitrogen-15, which captures a final proton and immediately splits into carbon-12 and helium-4, returning the carbon nucleus to begin the cycle again. The net result is identical to the proton-proton chain, converting 4 hydrogen nuclei into 1 helium nucleus, but the CNO cycle proceeds much more rapidly at higher temperatures, making it the dominant energy source in massive stars. The core of a main sequence star is an extraordinarily alien environment. Temperatures reach tens of millions of degrees, hot enough to strip atoms completely of their electrons, creating a plasma of bare nuclei and free electrons. The pressure is billions of times that of Earth's atmosphere, compressing matter to densities several times that of solid lead. In these conditions, normal matter behaves in ways that seem counterintuitive. Electrons become degenerate, a quantum mechanical effect, where the uncertainty principle prevents them from being compressed beyond a certain limit, creating a pressure that is independent of temperature. Photons scatter so frequently off the dense plasma that they take hundreds of thousands of years to random walk their way from the core to the surface, even though they travel at the speed of light. Outside, the core lies the radiative zone, a region where energy transport occurs primarily through radiation. Photons produced by fusion reactions in the core are absorbed and re-emitted countless times as they diffuse outward through this zone. The matter here is still dense enough that photons can travel only a tiny distance before being absorbed, making the radiative zone effectively opaque. The temperature decreases gradually with distance from the core, and the density falls as well, but conditions remain extreme by terrestrial standards throughout the inner portions of the star. In the Sun, the radiative zone extends from the core to about 70% of the solar radius, encompassing nearly half of the Sun's mass. Above the radiative zone, in cooler regions where the temperature has dropped below about 2 million degrees Celsius, convection becomes the primary means of energy transport. Here, the temperature gradient becomes steep enough that hot plasma becomes buoyant, rising toward the surface while cooler material sinks back down. This creates enormous convection cells, rivers of plasma flowing in complex patterns throughout the outer layers of the star. On the Sun's surface, these convection cells appear as the granulation pattern, polygonal cells averaging about 1,000 kilometers across, each one rising from below as hot plasma, releasing its energy to space, cooling and sinking back down, all within a period of about 10 minutes. Larger supergranulation cells, 30,000 kilometers across, organize these smaller granules into a larger-scale flow pattern that persists for a day or more. The surface of a main sequence star, called the photosphere, is the layer from which light can escape directly into space. Below the photosphere, the star is opaque. Above it, the gas becomes transparent. The photosphere is surprisingly thin, typically just a few hundred kilometers deep, less than 1,000th of the star's radius. Yet this is the layer we see when we observe stars. The temperature at the photosphere determines the star's color and spectral type. Hot O and B-type stars have photospheric temperatures above 10,000 degrees and appear blue or blue-white. A-type stars are white, F-type stars are yellow-white, G-type stars like our Sun are yellow, K-type stars are orange, and M-type stars are red, with photospheric temperatures below 4,000 degrees. This temperature sequence is the primary ordering principle of stellar classification, reflecting the fundamental relationship between a star's mass, core temperature, and energy output. Above the photosphere lies the chromosphere, a thin layer a few thousand kilometers deep where temperature actually increases with height, reaching about 20,000 degrees at its top. This temperature inversion, where outer layers are hotter than inner layers, seems to violate the normal flow of heat from hot to cold, but it is caused by the deposition of energy from magnetic fields and acoustic waves that propagate up from the convection zone below. The chromosphere is usually invisible, overwhelmed by the bright photosphere, but during solar eclipses or when observed with specialized filters, it appears as a thin reddish layer, its color caused by hydrogen emission at the hydrogen alpha wavelength. The outermost layer of a star's atmosphere is the corona, a tenuous region extending millions of kilometers into space where temperatures soar to millions of degrees. The corona is visible during total solar eclipses as a beautiful pearly white glow surrounding the darkened solar disk, but its high temperature was not understood until the mid-20th century and remains an active research topic. The coronal heating problem, as it is called, asks how the corona can be heated to such high temperatures when it lies above much cooler layers. The answer involves magnetic fields that emerge from the interior, threads of magnetic flux that carry energy upward and release it through various processes, including magnetic reconnection, wave dissipation, and nanoflares, small explosive energy releases occurring constantly throughout the corona. These same magnetic fields structure the corona into loops, arches, and streamers, and drive the solar wind, a continuous outflow of charged particles that fills the solar system and beyond. Stars on the main sequence exhibit a wide range of masses, from as little as 8% of the Sun's mass up to perhaps 200 solar masses, and this mass determines every other property. The most massive O-type stars are more than 1 million times as luminous as the Sun, with surface temperatures exceeding 40,000 degrees and lifetimes of just a few million years. They burn through their hydrogen fuel so rapidly that they barely reach a stable main sequence configuration before beginning to evolve toward their explosive deaths. At the other extreme, the least massive M-type red dwarfs are 10,000 times fainter than the Sun, with surface temperatures around 3,000 degrees and lifetimes exceeding 10 trillion years. These stars burn hydrogen so slowly and efficiently that they will outlive not only our Sun, but essentially all currently existing main sequence stars, continuing to shine long after the universe has evolved into a state utterly different from what we observe today. Chapter 5. Red Dwarfs, the Patient. Stars' red dwarfs, the smallest and coolest stars capable of sustaining hydrogen fusion, represent the most common type of star in the universe. Comprising perhaps 70 to 80% of all stars, they are the fundamental stellar population, yet none are visible to the naked eye from Earth despite their overwhelming numbers. This paradox arises from their intrinsic faintness. Even the nearest red dwarfs, like Proxima Centauri, require telescopes to observe. These stars occupy the lower end of the main sequence, with masses ranging from about 8% to 40 or 50% of the Sun's mass. Surface temperatures between 2,500 and 4,000 degrees Celsius, and luminosities from 1/10,000th to a few percent of the solar value. What they lack in individual brilliance, they compensate for in longevity and sheer abundance. The defining characteristic of red dwarfs is their extraordinarily efficient use of fuel. Unlike more massive stars, which burn only the hydrogen in their cores, red dwarfs are fully convective throughout their interiors. Convection currents mix material from the core to the surface and back again, ensuring that all of the star's hydrogen eventually makes its way to the central regions where fusion can occur. This complete mixing means that red dwarfs can fuse essentially all of their hydrogen, not just the 10 to 15% in the core that Sun-like stars utilize. Combined with their inherently slow fusion rate due to lower core temperatures and pressures, this gives red dwarfs lifetimes measured in trillions of years, far exceeding the current age of the universe of 13.8 billion years. The implications of these immense lifetimes are profound. Every red dwarf that has ever formed since the Big Bang is still on the main sequence today, still fusing hydrogen, essentially unchanged since its birth. No red dwarf has ever evolved off the main sequence, exhausted its fuel, or reached the end of its life. The universe is simply not old enough yet for even the oldest red dwarfs to have consumed their hydrogen. This means that observations of red dwarfs show us stars in their youth or early middle age, with the vast majority of their lives still ahead of them. In the far future, when the universe is hundreds of billions or trillions of years old, when star formation has ceased because galaxies have consumed their gas supplies, when all the massive stars have died and Sun-like stars have faded to white dwarfs, red dwarfs will still be shining, the last main sequence stars remaining, gradually working through their hydrogen fuel in the darkness. Despite their small size, red dwarfs can be extraordinarily active. Many exhibit powerful magnetic fields generated by dynamo action in their fully convective interiors, where the churning plasma creates and amplifies magnetic flux. These fields emerge at the surface, creating star spots analogous to sunspots, but sometimes covering substantial fractions of the stellar surface, dark regions where strong magnetic fields suppress convection and reduce the local temperature. The magnetic fields also drive powerful flares, sudden releases of stored magnetic energy that can temporarily increase the star's brightness by factors of 10 or more, particularly in ultraviolet and X-ray wavelengths. These flares release energetic particles and intense radiation that can have dramatic effects on any planets orbiting the red dwarf, potentially eroding atmospheres or sterilizing surfaces, raising questions about the habitability of planets in red dwarf systems. Red dwarf systems have become a focus of the search for potentially habitable exoplanets, both because red dwarfs are so numerous and because their low luminosity places their habitable zones, the orbital distances where liquid water could exist on a planet's surface, very close to the star. A planet in the habitable zone of a red dwarf might orbit at a distance of 1/10 or even 1/20th of an astronomical unit, far closer than Mercury orbits the Sun. This proximity creates unique conditions. The planet would likely be tidally locked, with one hemisphere perpetually facing the star and the other in eternal darkness, potentially creating extreme temperature differences between the day and night sides. The star would appear enormous in the sky of such a planet, perhaps 10 or 20 times the angular size of our Sun as seen from Earth, a huge red orb dominating the heavens. The light reaching the surface would be redder than sunlight, shifted toward longer wavelengths, which might affect photosynthesis or require different chemistry for life to capture the stellar energy efficiently. The close proximity of habitable zone planets to red dwarfs also means they are subjected to the star's most violent activity. During flares, the flux of ultraviolet and X-ray radiation can increase by factors of hundreds or thousands, bathing the planet in harmful high-energy photons. The stellar wind, though weaker than the Sun's, strikes the planet's magnetosphere at much closer range. For a planet to maintain a protective atmosphere and magnetic field over billions of years, it would need to be geologically active and possess a strong intrinsic magnetic field, requirements that may be difficult to satisfy for all but the most massive terrestrial planets. Yet the sheer number of red dwarfs, combined with observations showing that planets are common around them, means that even if only a small percentage of red dwarf planets are habitable, there could still be billions of potentially life-bearing worlds orbiting these small stars throughout the galaxy. The nearest red dwarfs to Earth offer valuable laboratories for studying these stars in detail. Proxima Centauri, at 4.2 light-years distance, is not only the nearest star but also hosts at least one confirmed planet, Proxima Centauri b, orbiting within the star's habitable zone. This planet, with a minimum mass about 20% greater than Earth's, orbits its star every 11 days at a distance of just 7.5 million kilometers, closer than Mercury's perihelion distance from the Sun. Whether Proxima b has an atmosphere, whether it hosts liquid water, whether it could potentially harbor life, remains unknown, but it represents the nearest exoplanet and thus a prime target for future detailed observations. Proxima Centauri itself is a flare star, exhibiting dramatic brightness variations and occasional outbursts that could impact any planet's habitability, making it a valuable case study for understanding red dwarf planet environments. Barnard's star, the second nearest star system at 6 light-years distance, is another well-studied red dwarf, slightly more massive and luminous than Proxima Centauri. Moving rapidly across the sky with the largest proper motion of any known star, Barnard's star will approach within about 3.8 light-years of the Sun in approximately 10,000 years before beginning to recede again. Long-term observations have revealed possible planetary companions, though confirmation remains challenging due to the star's low mass and the correspondingly small signals produced by orbiting planets. Like other red dwarfs, Barnard's star will continue burning for trillions of years, a stable beacon that will outlast essentially every other star currently visible from Earth. The evolutionary path of red dwarfs differs dramatically from that of more massive stars. When a red dwarf eventually exhausts its hydrogen fuel, after trillions of years, it will not expand into a red giant as the Sun will. Instead, it will gradually contract and heat, becoming a blue dwarf, a hypothetical stellar type that has never been observed because the universe is too young for any red dwarf to have reached this stage. The blue dwarf phase will last for perhaps another trillion years as the star burns the last remnants of its hydrogen, growing hotter and bluer before finally exhausting its fuel completely. At that point, lacking any fusion reactions to support it, the star will contract into a white dwarf, skipping entirely the red giant and planetary nebula phases that characterize the death of Sun-like stars. This white dwarf will be composed primarily of helium rather than the carbon and oxygen that make up white dwarfs formed from more massive stars, representing a different end state that will only become common in the distant future. The low luminosity of red dwarfs makes them difficult to detect at large distances, which introduces a significant observational bias into astronomical surveys. Most of the stars visible to the naked eye are intrinsically luminous giants and supergiants, rare massive stars that are visible across thousands of light years. The immediate solar neighborhood, within 10 or 20 light years of the Sun, provides a less biased sample, and surveys of this volume reveal that red dwarfs utterly dominate the stellar population. Within 12 light years of the Sun, there are approximately 50 known stars and brown dwarfs, of which 35 are red dwarfs, a percentage that likely reflects the galactic average. This suggests that the Milky Way contains hundreds of billions of red dwarfs, vastly outnumbering all other stellar types combined. Red dwarfs also play an important role in galactic chemical evolution. Although each red dwarf contains relatively little mass, their overwhelming numbers mean they collectively hold a significant fraction of the galaxy's stellar mass. Moreover, because they lock up their material for trillions of years, red dwarfs effectively remove gas from the cycle of star formation, death, and recycling that processes material through multiple generations of stars. Once gas collapses into a red dwarf, it will remain locked in that star essentially forever from the perspective of current galactic timescales. This makes red dwarfs a form of baryonic dark matter, visible matter that contributes to the total mass of galaxies, but does not participate in ongoing star formation or chemical enrichment. The study of red dwarfs continues to reveal surprises and complexities. Some red dwarfs rotate extremely rapidly, spinning once every few hours, which generates powerful magnetic fields and drives intense activity. Others are quiet and sedate, showing minimal variability. Some exist in binary or multiple systems, orbiting other red dwarfs or larger stars, while others drift alone through space. Some host planetary systems, while others appear solitary. This diversity suggests that red dwarf formation and evolution, while constrained by their low mass, still permits a range of outcomes depending on initial conditions, formation environment, and subsequent history. As telescopes and instruments improve, enabling more detailed studies of these faint but ubiquitous objects, our understanding of red dwarfs continues to deepen, revealing the complexity hidden in even the smallest stars. Chapter 6: Sun-like Stars, Yellow Dwarfs in the Cosmic Story. Sun-like stars, officially classified as G-type main sequence stars or yellow dwarfs, occupy a middle ground in stellar properties, neither the smallest nor the largest, neither the coolest nor the hottest, neither the longest-lived nor the shortest. Yet they hold special significance for humanity, as our own sun exemplifies this stellar class and provides the energy that powers Earth's biosphere and makes complex life possible. These stars have masses ranging from about 0.8 to 1.1 solar masses, surface temperatures between 5,000 and 6,000 degrees Celsius, and luminosities from about 0.5 to 1.5 times the sun's output. They shine with a warm yellow-white light that seems bright to our eyes, adapted as we are to solar illumination, and they will maintain their main sequence stability for approximately 8 to 12 billion years before evolving into red giants. Our sun, at 4.6 billion years old, is currently about halfway through its main sequence lifetime, a mature but not yet old star steadily fusing hydrogen into helium in its core. Every second, the sun converts approximately 600 million tons of hydrogen into 596 million tons of helium, with the missing 4 million tons transformed into energy according to Einstein's equation, producing an output of about 4 times 10 to the 26th watts. This energy radiates outward in all directions, and even though Earth intercepts only about 1/2 billionth of the total solar output, that tiny fraction is enough to drive our weather systems, power photosynthesis, maintain liquid water, and create the conditions necessary for life. The sun's stability over billions of years has been crucial for the development of life on Earth. A star that varied significantly in luminosity or underwent dramatic activity cycles might have rendered a planet's climate too unstable for complex ecosystems to evolve. The internal structure of the sun reveals the complexity hidden beneath its seemingly simple exterior. At the very center lies the core, extending to about 1/4 of the solar radius, but containing about half of the sun's total mass. Here, temperatures reach 15 million degrees Celsius and pressures exceed 200 billion times Earth's atmospheric pressure, creating conditions where the proton-proton chain proceeds efficiently. The energy density in the core, the power produced per unit volume, is actually rather modest, only about 270 watts per cubic meter, less than the metabolic heat production of a human body per unit volume. It is the sheer size of the sun, containing over 1 trillion trillion cubic meters of material that leads to the enormous total energy output. Surrounding the core, the radiative zone extends outward to about 70% of the solar radius. Throughout this zone, energy transport occurs through radiative diffusion, with photons slowly working their way outward through countless absorption and emission events. A photon produced in the core will take approximately 170,000 years to random walk its way to the base of the convection zone, traveling a straight-line distance of just 500,000 kilometers, but following a jagged path of many trillions of kilometers as it bounces randomly through the dense solar interior. During this journey, the photon's energy is gradually converted from high-energy gamma rays into lower-energy photons, including visible light, through the absorption and re-emission processes that dominate radiative transport. The outer layer of the Sun's interior, the convection zone, comprises the outer 30% of the solar radius but contains only about 2% of the solar mass. Here, the temperature has dropped to about 2 million degrees at the base of the zone and continues falling to about 5,800 degrees at the photosphere. The steep temperature gradient makes the region unstable to convection, causing hot plasma to rise while cooler material sinks, creating the granulation pattern visible on the solar surface. These convection cells transport energy much more efficiently than radiation, carrying about 90% of the solar energy output through the outer layers. The turbulent motion of the convective plasma also generates the Sun's magnetic field through dynamo action, creating the complex magnetic structures that produce sunspots, solar flares, coronal mass ejections, and the 11-year solar activity cycle. The solar activity cycle, first recognized from historical sunspot observations, reflects a periodic reversal of the Sun's global magnetic field. During solar minimum, sunspots are rare or absent, solar flares are infrequent, and the corona is relatively quiet and structured. As the cycle progresses toward solar maximum, magnetic activity increases dramatically. Sunspots appear in greater numbers, flares and coronal mass ejections become common, and the corona becomes more dynamic and turbulent. After reaching maximum, activity gradually declines toward the next minimum, completing a cycle that averages 11 years, but can range from 9 to 13 years. The underlying cause is the solar dynamo, where differential rotation, the fact that the Sun rotates faster at the equator than at the poles, stretches and amplifies magnetic field lines, creating increasingly complex magnetic structures that eventually become unstable, release their energy, and reset the cycle. Solar flares, sudden releases of magnetic energy stored in the coronal magnetic field, can release as much energy as millions of hydrogen bombs in just a few minutes. During a flare, plasma is heated to tens of millions of degrees, far hotter than the normal corona, and particles are accelerated to significant fractions of the speed of light. The energy is released primarily as X-rays and extreme ultraviolet radiation, which can ionize Earth's upper atmosphere when the flare is directed toward our planet, disrupting radio communications and GPS signals. The largest flares, classified as X-class events, can be detected across the electromagnetic spectrum from radio waves through gamma rays, demonstrating the tremendous energies involved in these magnetic reconnection events. Coronal mass ejections represent even larger releases of solar material and magnetic field, hurling billions of tons of plasma into space at speeds of hundreds to thousands of kilometers per second. When a coronal mass ejection is directed toward Earth and strikes our magnetosphere, it can trigger geomagnetic storms that create spectacular auroral displays at high latitudes, while also potentially damaging satellites, disrupting power grids, and interfering with various technologies. The most powerful geomagnetic storm in recorded history, the Carrington event of 1859, caused telegraph systems to fail, gave operators electric shocks, and produced auroras visible at tropical latitudes. If a similar event struck today, in our more technologically dependent society, the consequences could be far more severe, potentially causing trillions of dollars in damage and requiring years for full recovery. The sun's influence extends far beyond the photosphere through the solar wind, a continuous outflow of charged particles that fills the solar system and creates a vast bubble called the heliosphere. The solar wind originates in the corona, where the high temperature gives particles enough energy to escape the sun's gravity and flow outward at typical speeds of 400 to 800 kilometers per second. This supersonic flow carries the solar magnetic field with it, creating the interplanetary magnetic field that permeates the space between planets. The solar wind continues outward until it encounters the interstellar medium, the tenuous gas between stars, at a distance of more than 100 astronomical units from the sun. Here, the wind slows and deflects, creating the heliosheath and eventually the heliopause, the boundary where the solar wind's influence ends and true interstellar space begins. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Sun-like stars throughout the galaxy should exhibit similar behavior, with convection zones generating magnetic fields, activity cycles producing flares and coronal mass ejections, and stellar winds filling space around them. The details will vary with each star's age, rotation rate, and other properties. Young sun-like stars recently arrived on the main sequence typically rotate much faster than the EPAR present-day sun, completing a rotation in just a few days rather than the sun's 25-day equatorial period. This rapid rotation drives much stronger magnetic activity, producing more frequent and powerful flares and maintaining coronae hundreds of times more luminous in X-rays than the sun's. As these stars age, they gradually spin down, losing angular momentum to their stellar winds through magnetic braking, and their activity levels decline correspondingly. The sun itself was likely far more active billions of years ago, which may have had significant effects on the early Earth's atmosphere and the development of life. The question of whether sun-like stars commonly host planetary systems remained unanswered until the 1990s, when the first exoplanets were discovered around mature main-sequence stars. Since then, observations have revealed that planets are ubiquitous, with sun-like stars frequently hosting multiple planets in diverse configurations. Some systems resemble our solar system, with small, rocky planets close in and gas giants farther out, but many others exhibit architectures completely unlike our own, with massive hot Jupiters orbiting very close to their stars, systems of multiple super-Earths packed into tight orbits, or gas giants in eccentric orbits that cross through the habitable zone. This diversity suggests that planet formation, while common, produces a wide range of outcomes depending on the detailed conditions in the protoplanetary disk and the subsequent dynamical evolution of the system. The habitable zone around sun-like stars, the region where a planet's surface could maintain liquid water under the right atmospheric conditions, typically extends from about 9/10 to 1.5 astronomical units, encompassing Earth's orbit comfortably within its boundaries. This distance balances the need for sufficient stellar heating to prevent permanent freezing against the danger of excessive heating that would lead to a runaway greenhouse effect and the loss of water to space. Earth's position at 1 astronomical unit places it well within this zone, receiving enough energy for a temperate climate while avoiding the extremes that render Venus too hot and Mars too cold for surface liquid water under current conditions. The exact boundaries of the habitable zone depend on many factors, including the planet's atmospheric composition, albedo, greenhouse gas concentrations, and geological activity, making habitability a complex question that cannot be determined by orbital distance alone. Sun-like stars will eventually exhaust the hydrogen in their cores, typically after 10 to 12 billion years on the main sequence. When this occurs, the core, now composed of inert helium unable to fuse at these temperatures, will contract and heat while hydrogen fusion continues in a shell surrounding the core. This shell burning produces more energy than the core fusion did, causing the star to expand dramatically into a red giant, growing to perhaps 100 times its current radius while cooling at the surface. The Sun's red giant phase, beginning approximately 5 billion years from now, will have profound consequences for the inner solar system, with the expanding photosphere engulfing Mercury, Venus, and possibly Earth. while the increased luminosity boils away any remaining atmospheres and oceans. This transformation from yellow dwarf to red giant marks the end of the main sequence and the beginning of the final stages of stellar evolution. Chapter 7. Blue giants and supergiants, the bright and brief. At the opposite end of the stellar spectrum from red dwarfs lie the massive blue giants and supergiants, stars so luminous and hot that they reshape their surroundings, so energetic that they burn through their fuel in cosmically brief moments, so powerful that their deaths seed the cosmos with heavy elements and leave behind exotic remnants. These stars have masses exceeding 8 or 10 solar masses, surface temperatures above 10,000 and often exceeding 30 or 40,000 degrees Celsius, and luminosities ranging from thousands to millions of times the sun's output. They shine with an intense blue-white light, appearing bright even across vast distances, making them visible as individual beacons throughout the galaxy, and even in nearby galaxies millions of light-years away. Yet, despite their brilliance, or perhaps because of it, they are exceedingly rare, comprising less than 1% of all stars, and they live for just a few million to a few 100 million years before their spectacular demise. The enormous mass of blue giants leads directly to their extreme properties through the relentless logic of stellar physics. More mass means stronger gravity, which compresses the core to higher densities and temperatures, which accelerates fusion reactions, which produces more energy. The luminosity of a star scales roughly as the mass raised to the third or fourth power, meaning a star 10 times the sun's mass is not 10 times as luminous, but rather 1,000 to 10,000 times as luminous. This extreme sensitivity means that the most massive stars are profoundly different from lower mass stars, operating under conditions so extreme that different physical processes dominate their behavior. Their cores reach temperatures of 50 to 100 million degrees, hot enough that the CNO cycle, barely relevant in the Sun, becomes the primary and overwhelmingly dominant fusion mechanism. The internal structure of massive stars differs fundamentally from that of Sun-like stars. The core, where temperatures and pressures are highest, is where hydrogen fuses into helium through the CNO cycle. This fusion process is far more temperature sensitive than the proton-proton chain, scaling as temperature to the 16th or 17th power rather than temperature to the 4th power. This extreme temperature sensitivity means that fusion is concentrated in a small central region, and any slight increase in temperature causes a dramatic increase in fusion rate. The core responds by developing a steep temperature gradient and becoming convective, with hot material rising from the center and cooler material sinking back, mixing the core and transporting energy outward efficiently. Surrounding the convective core is a radiative envelope that extends to the surface, the opposite arrangement from Sun-like stars, which have radiative cores and convective envelopes. The surfaces of blue giants and supergiants are dramatically different from the Sun's photosphere. The extreme luminosity means that radiation pressure, the outward force exerted by photons streaming from the interior, becomes significant and even dominant over gas pressure in the outer layers. This radiation pressure drives powerful stellar winds, continuous outflows of matter from the stellar surface, carrying away mass at rates of 1/1,000,000th to 1/10,000th of a solar mass per year, millions of times stronger than the sun's wind. These winds reach velocities of thousands of kilometers per second, fast enough to escape the star's gravity permanently and carry material far into space. Over a star's main sequence lifetime, these winds can remove a significant fraction of the star's initial mass, sometimes 20 or 30% or more, depositing enriched material into the interstellar medium and affecting the star's subsequent evolution. The combination of high luminosity and strong stellar winds means that massive stars profoundly affect their surroundings. A single massive star can ionize a region of space hundreds of light years across, creating an emission nebula where the ultraviolet radiation from the star strips electrons from hydrogen atoms and the electrons recombine with protons, emitting the characteristic red light of hydrogen alpha that gives nebulae their color. The stellar wind sweeps up surrounding gas, creating expanding bubbles and shells that compress the interstellar medium. Multiple massive stars working together in a young star cluster can evacuate an enormous cavity, blowing away the molecular cloud that gave birth to them and exposing the stars themselves to optical observation. The Orion Nebula, illuminated primarily by the four massive stars of the Trapezium cluster, exemplifies this process, showing a molecular cloud being sculpted and eroded by the fierce radiation and winds from young massive stars. Despite their immense energy output, massive stars are surprisingly unstable compared to lower mass stars. The extreme temperature sensitivity of the CNO cycle means that the core operates near a critical point where small perturbations can cause large changes in energy production. The star maintains equilibrium through adjustments in structure and energy transport, but this equilibrium can be precarious. Some massive stars exhibit variability, changing brightness over periods of days, weeks, or years as they oscillate or undergo instabilities in their outer layers. The most luminous massive stars approach or exceed the Eddington limit, the theoretical boundary where radiation pressure equals gravitational force, beyond which radiation pressure would blow the star apart. Stars near this limit are inherently unstable, prone to eruptions and mass loss events that can temporarily increase their brightness dramatically. Luminous blue variables represent an extreme form of massive star variability. These stars, among the most luminous known, with masses of 50 to 100 solar masses or more and luminosities exceeding 1,000,000 times the Sun's, undergo irregular eruptions during which they can brighten by 1 to 3 magnitudes, eject substantial amounts of mass, and create circumstellar nebulae from their expelled material. Eta Carinae, the most famous example, underwent a great eruption in the 1840s, during which it briefly became the second brightest star in the sky despite lying more than 7,000 light-years away. The eruption ejected several solar masses of material, creating the homunculus nebula that now surrounds the star, a bipolar structure of dust and gas still expanding outward from the violent event. The mechanism driving these eruptions remains uncertain, possibly involving instabilities near the Eddington limit or interactions in a binary system, but they demonstrate the extreme conditions under which the most massive stars operate. Blue supergiants occupy a particular phase of massive star evolution. After a massive star exhausts the hydrogen in its core and begins shell burning, it typically expands and cools, becoming a red supergiant with a bloated envelope and a cool, low-density surface. However, depending on the star's mass, rotation, metallicity, and mass loss history, it may instead evolve into a blue supergiant, maintaining a hotter surface temperature and more compact structure. Blue supergiants can also result from red supergiants that have lost substantial envelope mass through winds, exposing deeper, hotter layers. The most famous blue supergiant, Rigel in the constellation Orion, shines with a luminosity over 100,000 times the Sun's, despite lying approximately 900 light-years away, making it one of the most luminous stars visible to the naked eye. The evolution of massive stars proceeds much more rapidly than that of lower mass stars, constrained by their profligate consumption of nuclear fuel. A star of 20 solar masses, burning fuel approximately 30,000 times faster than the Sun, but containing only 20 times as much fuel, will exhaust its core hydrogen in just a few million years instead of billions. After hydrogen depletion, the star begins a complex series of evolutionary phases, burning heavier elements in successive shells and cores, each phase shorter than the last. Helium fuses into carbon in the core, while hydrogen burns in a shell, lasting perhaps 1,000,000 years. Then carbon burns to neon, oxygen, and magnesium for a few thousand years. Neon burns for a few years, oxygen burns for a few months, silicon burns into iron group elements over a few days. Each stage releases less energy per unit mass than the previous stage, and each requires higher temperatures to proceed, creating an onion-like structure of nested shells surrounding an inert iron core. The iron core represents an endpoint, a dead end in stellar nucleosynthesis. Iron has the highest binding energy per nucleon of any element, meaning that fusing iron into heavier elements consumes energy rather than releasing it. When the iron core grows to approximately 1.4 solar masses, the Chandrasekhar limit, Electron degeneracy pressure can no longer support it against gravity. The core collapses catastrophically in less than a second, falling inward at velocities approaching 1/4 the speed of light, compressing matter to nuclear density and beyond. The collapse releases a tremendous amount of gravitational potential energy, comparable to all the energy the star has produced through fusion over its entire life, but released in seconds rather than millions of years. Most of this energy goes into neutrinos, which flood outward from the collapsing core, but a small fraction, about 1%, goes into blast energy that drives the outer layers of the star into space in a supernova explosion. The main sequence phase of massive stars, despite its brevity, is critical for understanding cosmic evolution. These stars are the primary factories for elements heavier than helium, synthesizing carbon, nitrogen, oxygen, and heavier elements through fusion reactions and distributing them through stellar winds and eventual supernova explosions. They ionize and heat the interstellar medium, creating emission nebulae and affecting the thermal structure of galaxies. They trigger new episodes of star formation by compressing molecular clouds with their winds and supernova shockwaves. They end their lives leaving behind neutron stars and black holes, exotic objects that continue to influence their surroundings long after the star itself has vanished. Despite their rarity, massive stars play roles in galactic ecology completely disproportionate to their numbers, shaping the chemical and physical evolution of galaxies in ways that persist for billions of years after the stars themselves have died. Chapter 8: The Cycles of Stellar Life. The life of a star, from birth to death, follows pathways determined primarily by its initial mass, with secondary influences from composition, rotation, and whether it exists in a binary system. This journey through the Hertzsprung-Russell diagram, the fundamental chart that plots stellar luminosity against temperature, traces an evolutionary track unique to each mass range, yet following predictable patterns that reveal the underlying physics governing stellar behavior. Understanding these life cycles provides insight into the past, present, and future of every star in the cosmos, from the smallest red dwarf that will shine for trillions of years to the most massive supergiant that races through its existence in mere millions. For stars of the lowest masses, below about half a solar mass, the life cycle is remarkably simple. These red dwarfs undergo a long main sequence phase lasting trillions of years, during which they fuse hydrogen throughout their fully convective interiors. When they finally exhaust their hydrogen, so far in the future that no such star has yet reached this stage, they will contract and heat, becoming blue dwarfs for another trillion years or so before settling into white dwarf status. The entire process occurs without the dramatic expansion into a red giant phase or the explosive death that characterizes more massive stars. These stars simply fade gradually, transitioning from active fusion to degeneracy-supported remnants without fanfare, their long lives ending not with bangs but with whimpers stretched across incomprehensible timespan S. Stars with masses between about half a solar mass and 8 or 9 solar masses, including our Sun, follow more complex paths. After their main sequence phase, lasting from hundreds of millions to tens of billions of years depending on mass, these stars exhaust the hydrogen in their cores and begin the transition to red giants. The core, now composed of inert helium, contracts and heats while hydrogen continues burning in a shell around it. This shell burning produces more energy than the core fusion did, and the star responds by expanding dramatically, its outer layers swelling to tens or hundreds of times the original radius while cooling at the surface, shifting from yellow or white to orange or red. During this red giant phase, the star can become thousands of times more luminous than during its main sequence life, even though its surface has cooled, because the vastly increased surface area more than compensates for the lower temperature per unit area. As the core contracts, it heats until eventually, when the temperature reaches about 100 million degrees Celsius, helium begins to fuse into carbon through the triple alpha process, where 3 helium nuclei combine in quick succession to form carbon. For stars near the lower mass limit, around half a solar mass, the core, when helium ignition occurs, is supported by electron degeneracy pressure, a quantum mechanical effect that makes the core resistant to expansion. When fusion begins in such a degenerate core, the energy released cannot immediately expand and cool the core, so the temperature rises rapidly, the fusion rate accelerates exponentially, and a helium flash occurs, a brief period of intense helium fusion during which the core produces more energy than the entire rest of the galaxy. However, this energy goes into lifting the degeneracy and expanding the core rather than being radiated away, so the flash is not visible from outside the star. The core quickly reaches equilibrium with non-degenerate helium fusion, and the star settles into a relatively stable phase, burning helium in its core and hydrogen in a surrounding shell. For somewhat more massive stars, including the Sun, the core is not quite degenerate when helium ignition occurs, and the transition from helium inert to helium burning happens more smoothly without a dramatic flash. Either way, the star then spends some time, perhaps 10% of its main sequence lifetime, burning helium into carbon while still maintaining its red giant configuration. The details depend on mass and composition, but eventually the helium in the core is exhausted, leaving an inert core of carbon and oxygen. The star then begins shell burning again, now with helium burning in a shell around the core and hydrogen burning in a shell outside that, and enters a phase called the asymptotic giant branch, or AGB. AGB stars are among the most luminous red giants, and they exhibit behavior quite different from earlier red giant phases. The double shell burning is thermally unstable, causing the star to pulse with periods of tens to hundreds of days, swelling and shrinking rhythmically as the shells alternately burn strongly and weakly. These pulsations drive powerful stellar winds that carry away the outer envelope of the star at increasing rates, eventually ejecting most of the remaining envelope mass into space. The mass loss creates an expanding circumstellar envelope of gas and dust around the star, gradually revealing the hot core within. Eventually, after perhaps 1 million years on the AGB, the envelope is entirely lost and the remaining core, still burning hydrogen and helium in shells around an inert carbon-oxygen center, is exposed. This hot core, with temperatures of tens of thousands of degrees, ionizes the previously ejected envelope, causing it to fluoresce and become visible as a planetary nebula, a glowing shell of gas expanding away from the central star. Planetary nebulae, despite their name, which arises from their resemblance to planetary disks when viewed through early telescopes, have nothing to do with planets. They are the final gasps of sun-like stars, the ejected envelopes illuminated by ultraviolet radiation from the dying star at their centers. These nebulae display a stunning variety of shapes and structures, from simple spherical shells to complex bipolar structures, from ring-shaped nebulae to irregular chaotic clouds. The morphology depends on the star's rotation, magnetic fields, whether it was in a binary system, and how mass loss proceeded during the AGB phase. Some planetary nebulae show clear evidence of multiple shells ejected at different times, creating nested structures. Others show jets, onset, and knots that indicate collimated outflows and instabilities in the ejection process. The central stars of planetary nebulae are among the hottest stars known, with surface temperatures sometimes exceeding 100,000 degrees as the exposed core continues burning its shells and slowly contracts toward white dwarf status. The planetary nebula phase lasts only tens of thousands of years, a cosmically brief moment during which the envelope expands, thins, and eventually disperses into the interstellar medium, merging with the general gas between stars and enriching it with carbon, nitrogen, oxygen, and other elements synthesized during the star's life. Meanwhile, the central star, having exhausted all possible fusion reactions, contracts into a white dwarf, an object about the size of Earth but containing roughly half the mass of the original star, now supported entirely by electron degeneracy pressure. The white dwarf no longer generates energy through fusion, but shines simply from its residual heat, cooling gradually over billions of years, fading from white to yellow to red to ultimately a cold, dark black dwarf, though the universe is not yet old enough for any black dwarfs to exist. More massive stars, those exceeding 8 to 10 solar masses, follow dramatically different paths. After their relatively brief main sequence phases, they evolve through red supergiant phases, burning heavier and heavier elements in their cores while maintaining enormous distended envelopes. Unlike lower mass stars, these massive stars can achieve core temperatures sufficient to fuse carbon into neon, neon into oxygen, oxygen into silicon, and silicon into iron group elements. Each successive burning stage occurs more rapidly and releases less energy per unit mass than the previous one, creating the onion-like shell structure with iron at the center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen in the outermost burning shell. The evolution through these advanced burning stages happens with shocking rapidity. A 20 solar mass star might spend 6 million years on the main sequence burning hydrogen, then 1 million years burning helium, then 12,000 years burning carbon, 3 years burning neon, a year burning oxygen, and finally, just a few days burning silicon into iron. This extreme acceleration reflects the declining energy yield from fusion of heavier elements and the increasing energy losses through neutrino emission from the superhot core. When silicon burning nears completion, the star has only days left before its core reaches the Chandrasekhar limit and collapses. The core collapse and subsequent supernova explosion represent the most dramatic death possible for a star, a cataclysmic event that we will explore in greater detail later. For now, we note that the explosion ejects most of the star's mass into space at velocities of thousands to tens of thousands of kilometers per second, seeding the interstellar medium with heavy elements and creating expanding shock waves that trigger new star formation. The core survives, compressed either into a neutron star, an object 20 kilometers across containing 1 to 3 solar masses held up by neutron degeneracy pressure, or into a black hole if the collapsing core exceeded about 3 solar masses. The stellar life cycle is thus intimately connected to the cosmic cycle of matter. Stars are born from molecular clouds enriched by previous generations of stars. They synthesize heavier elements through fusion reactions. They return material to the interstellar medium through stellar winds and planetary nebulae or supernova explosions. The next generation of stars forms from this enriched material, containing more heavy elements, which affects their properties and evolution. Over cosmic time, galaxies have gradually increased their metallicity, the fraction of elements heavier than helium, from nearly 0 shortly after the Big Bang to approximately 2% in solar neighborhood gas today. This chemical evolution is driven primarily by stellar nucleosynthesis and the return of processed material to the interstellar medium, a process that has been operating for over 13 billion years and continues today in star-forming regions throughout the universe. Chapter 9. Fusion. The stellar forge. Nuclear fusion, the process by which light atomic nuclei combine to form heavier nuclei while releasing energy, is the fundamental power source for stars and the mechanism by which the universe creates all elements heavier than lithium. Understanding fusion requires delving into nuclear physics, quantum mechanics, and thermodynamics, examining how conditions in stellar interiors enable reactions that would be impossible under terrestrial conditions, and exploring the various fusion pathways that operate at different temperatures and in different types of stars. Fusion is not merely an energy source, but a creative process, the stellar forge that transforms the primordial hydrogen and helium from the Big Bang into the rich diversity of elements that make up planets, life, and everything in the material universe. At its most fundamental level, fusion occurs when atomic nuclei approach each other closely enough that the strong nuclear force, which binds protons and neutrons together inside nuclei, can overcome the electrostatic repulsion between positively charged nuclei. The strong force is indeed strong, approximately 100 times more powerful than the electromagnetic force at very short ranges, but it operates only over distances comparable to the size of a nucleus, about 1 femtometer or 1 quadrillionth of a meter. At larger distances, the electromagnetic force dominates, and like-charged nuclei repel each other with a force that increases as they approach. This creates an energy barrier called the Coulomb barrier that nuclei must overcome to fuse, and overcoming this barrier requires either tremendous velocities corresponding to high temperatures or quantum mechanical tunneling through the barrier. In stellar cores, both mechanisms operate. The high, the IC temperatures, measured in millions or tens of millions of degrees, give nuclei kinetic energies measured in thousands of electron volts, a tiny fraction of the energy needed to classically overcome the Coulomb barrier, yet sufficient when combined with quantum tunneling. According to quantum mechanics, particles can probabilistically tunnel through energy barriers that would be insurmountable classically, appearing on the other side even though they never possessed enough energy to climb over the top. The probability of tunneling depends exponentially on the barrier height and width, which in turn depend on the charges of the nuclei involved and their relative energy. In stellar conditions, even though most collisions between nuclei fail to result in fusion, the vast number of nuclei and the enormous number of collisions occurring every second means that fusion reactions proceed at rates sufficient to power the star. The simplest fusion reaction is the combining of two protons to form a deuteron, the nucleus of deuterium consisting of one proton and one neutron. However, this reaction cannot occur through the strong force alone because there is no stable nucleus consisting of two protons. Instead, one of the protons must undergo beta plus decay during the collision, converting into a neutron and emitting a positron and a neutrino. This process involves the weak nuclear force, one of the fundamental forces of nature responsible for certain types of radioactive decay, and it is extraordinarily unlikely for any given collision. The average proton in the Sun's core will collide with other protons billions of times every second for billions of years before undergoing this reaction. Yet with approximately 10 to the 57 protons in the Sun's core, even this vanishingly small probability results in about 10 to the 38 reactions per second, producing the energy that powers the Sun. Once formed, the deuteron quickly captures another proton to form helium-3, a light isotope of helium with two protons and one neutron. This reaction proceeds through the strong force and occurs much more readily than the initial proton-proton fusion. The helium-3 nucleus is stable and can persist for millions of years in the core before encountering another helium-3 nucleus, at which point the two fuse to form helium-4, releasing two protons in the process. This sequence, called the proton-proton chain, is the dominant fusion process in stars with core temperatures below about 18 million degrees Celsius, including the Sun and all lower mass stars. The net result is that four protons are converted into one helium-4 nucleus, two positrons, two neutrinos, and two gamma-ray photons, with the mass difference between the initial and final products appearing as kinetic energy of the products. In hotter cores, above approximately 18 million degrees, an alternative pathway becomes dominant, the CNO cycle, first proposed by Carl Friedrich von Weizsäcker and Hans Bethe in the late 1930s. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts that facilitate the conversion of hydrogen to helium. The cycle begins when a carbon-12 nucleus captures a proton, forming nitrogen-13, which beta decays to carbon-13 while emitting a positron and a neutrino. The carbon-13 captures another proton to become nitrogen-14, which captures a third proton to form oxygen-15. The oxygen-15 beta decays to nitrogen-15, which captures a fourth proton and immediately splits into carbon-12 and helium-4. The carbon-12 nucleus is identical to the one that started the cycle, ready to begin again, while the helium-4 nucleus represents the fusion of four protons, just as in the proton-proton chain. The CNO cycle proceeds much more rapidly than the proton-proton chain at higher temperatures because the reactions involved have different energy dependencies. The rate-limiting step in the proton-proton chain is the initial proton-proton fusion involving the weak force, which is largely independent of temperature. The CNO cycle, however, involves only strong and electromagnetic interactions for most steps, with rates that depend strongly on temperature, scaling approximately as temperature to the 16th power. This extreme temperature sensitivity means that in massive stars with core temperatures of 30 or 40 million degrees, the CNO cycle completely dominates energy production. While in the Sun, with its core temperature of 15 million degrees, the proton-proton chain produces about 99% of the energy, with only 1% from the CNO cycle. After stars exhaust their core hydrogen, those massive enough to heat their cores sufficiently can begin fusing helium into heavier elements through the triple alpha process. This reaction must overcome a seemingly insurmountable obstacle. There are no stable nuclei with mass numbers 5 or 8. When two helium-4 nuclei collide, they briefly form beryllium-8, but this nucleus is unstable and decays back into two helium nuclei in about 10 to the minus 16 seconds. However, at temperatures above 100 million degrees and densities of 100,000 grams per cubic centimeter, conditions found in the cores of red giants, the beryllium-8 concentration, though tiny, is sufficient that occasionally a third helium nucleus collides with a beryllium-8 before it decays, forming carbon-12. This three-body reaction, requiring three particles to interact essentially simultaneously, would be impossibly rare except for a remarkable coincidence. The carbon-12 nucleus has an excited energy level at precisely the right energy to be formed through the triple alpha process, a state known as the Hoyle state after Fred Hoyle, who predicted its existence in 1953 based on the fact that carbon exists in the universe. This resonance increases the reaction rate by many orders of magnitude, making carbon production efficient enough to power red giants and produce the carbon essential for life. The formation of carbon through this process, depending as it does on this apparently fine-tuned resonance, has been cited as evidence of anthropic selection in physics, the idea that the universe's properties must be compatible with the emergence of observers who can measure them. Whether this represents profound insight or mere tautology remains debated, but the triple alpha process certainly represents a crucial link in the chain of nucleosynthesis that leads from hydrogen to the complexity of chemistry. Once carbon exists in stellar cores, it can participate in further fusion reactions. At temperatures above 600 million degrees, carbon nuclei can fuse with helium to form oxygen, or two carbon nuclei can fuse to form neon, sodium, or magnesium, depending on the specific reaction pathway. Neon burning, occurring above 1 billion degrees, involves the photodisintegration of neon by high-energy gamma rays, breaking it apart into oxygen and helium, which then reacts with another neon nucleus to form magnesium. Oxygen burning around 1.5 billion degrees produces silicon, phosphorus, and sulfur. Silicon burning, the final fusion stage, occurs at temperatures above 3 billion degrees, and involves a complex network of reactions where silicon nuclei are built up through sequential addition of helium nuclei, producing iron group elements. Each successive burning stage yields less energy per unit mass than the previous stage, a consequence of the increasing binding energy per nucleon as we move toward iron. Hydrogen fusion releases about 7 million electron volts per nucleon, providing about 0.7% mass energy conversion. Helium fusion to carbon releases about 0.1%. Carbon to neon releases still less. By the time silicon fuses to iron, the energy release has dropped to a tiny fraction of a percent, barely sufficient to support the star against gravity and occurring so rapidly that the silicon burning phase lasts only days in a massive star. Iron represents the endpoint because it has the highest binding energy per nucleon of all elements. Fusing iron into heavier elements requires energy input rather than releasing energy, making it thermodynamically unfavorable under stellar conditions. The fusion processes in stars create elements up to iron through successive burning stages in the cores and shells of massive stars. Elements heavier than iron cannot be produced efficiently through fusion, but instead form through neutron capture processes. When free neutrons, produced as byproducts of various reactions in stellar interiors, are captured by existing nuclei, the nuclei become heavier isotopes of the same element. If these isotopes are unstable, they undergo beta decay, converting a neutron into a proton and moving one element higher in the periodic table. This process can build up heavy elements through two main pathways: the slow, or S process, occurring over thousands of years in the interiors of AGB stars where neutron densities are relatively low, and the rapid, or R process, occurring in seconds during supernova explosions or neutron star mergers where neutron densities are extremely high. The S process produces about half of the elements heavier than iron, including much of the lead, barium, strontium, and other elements that form through slow neutron capture, allowing each unstable isotope to beta decay before capturing another neutron. The R process produces the other half, including the heaviest stable elements and all the elements heavier than bismuth, which have no stable isotopes. The R process requires such extreme neutron densities that nuclei capture many neutrons before decaying, building up very neutron-rich isotopes far from the valley of stability, which then beta decay back toward stable configurations after the neutron flux ends. Recent observations of gravitational waves from neutron star mergers, combined with subsequent electromagnetic observations showing the production of heavy elements in the merger ejecta, have confirmed that neutron star mergers are important sites for R-process nucleosynthesis, possibly producing most of the gold, platinum, uranium, and other heavy elements in the universe. The neutrinos produced as byproducts of fusion reactions offer a unique window into stellar cores. Unlike photons, which scatter countless times and take hundreds of thousands of years to escape from the sun's core, neutrinos interact so weakly with matter that they stream directly outward at nearly the speed of light, escaping the sun in just 2 seconds and reaching Earth 8 minutes later. Solar neutrino observatories, using vast tanks of cleaning fluid, water, or other materials buried deep underground to shield from cosmic rays, can detect these neutrinos and thus observe fusion reactions occurring in the sun's core right now, not hundreds of thousands of years ago as photons reveal. The observation of solar neutrinos in numbers matching theoretical predictions provides direct confirmation that the sun is indeed powered by nuclear fusion and that our understanding of stellar structure is fundamentally correct. Fusion in stars represents one of the universe's most important processes, converting the simple into the complex, releasing energy that lights the cosmos, and creating the chemical diversity that makes planets and life possible. Every carbon atom in our bodies, every oxygen atom in the water we drink, every calcium atom in our bones, every iron atom in our blood was forged in the core of a star, either through fusion or through neutron capture processes powered ultimately by fusion. We are, quite literally, made of star stuff, as Carl Sagan eloquently noted, the ashes of long-dead stars recycled through successive generations into planets and organisms. The fusion reactions that power stars connect us directly to the cosmos, linking the physics of atomic nuclei to the grandest questions of cosmic evolution and our own existence. Chapter 10: The Deaths of Stars, White Dwarfs. When low and intermediate mass stars exhaust their fusion fuel and shed their outer envelopes as planetary nebulae, they leave behind dense cores of carbon and oxygen approximately the size of Earth but containing masses comparable to the Sun. These stellar remnants, called white dwarfs, represent the evolutionary endpoint for more than 97% of all stars, including our Sun, which will become a white dwarf approximately 7.5 billion years from now. White dwarfs are peculiar objects, glowing from residual heat but generating no new energy, supported against gravitational collapse not by thermal pressure, but by a quantum mechanical effect, and slowly cooling over billions of years toward darkness. They mark the transition from active star to stellar corpse, still luminous but inexorably fading, no longer participants in the creative cycle of fusion, but merely monuments to stellar lives now ended. The physics of white dwarfs differs fundamentally from that of normal stars. In a main sequence star, gas pressure from thermal motion of particles provides the support against gravity, with hotter cores producing more pressure and thus supporting larger masses. In a white dwarf, the matter is compressed to such extreme densities, typically 1 million times the density of water or 1 ton per cubic centimeter, that quantum mechanics dominates the behavior of electrons. According to the Pauli exclusion principle, no two electrons can occupy exactly the same quantum state, which includes having the same position and momentum. As matter is compressed and electrons are forced into smaller volumes, they must occupy higher and higher momentum states, creating a pressure called electron degeneracy pressure that depends only on density, not on temperature. This temperature independence has profound consequences. Unlike a normal star, where compression leads to heating, which increases pressure and halts the compression, a white dwarf's degeneracy pressure does not increase with temperature. The white dwarf can cool without contracting, radiating away its thermal energy while maintaining constant radius. Conversely, adding mass to a white dwarf does not cause it to expand, as would happen with a normal star, but instead causes it to contract, increasing the density and thus the degeneracy pressure until equilibrium is restored at a smaller radius. This counterintuitive mass-radius relationship means that more massive white dwarfs are smaller, with the most massive white dwarfs being roughly half the diameter of the least massive. There exists a maximum mass for white dwarfs, discovered theoretically by Subrahmanyan Chandrasekhar in 1930 while still a graduate student. The Chandrasekhar limit, approximately 1.4 solar masses, arises because as white dwarfs become more massive and thus denser, the electrons must occupy increasingly high momentum states to satisfy the exclusion principle. Eventually, the electrons become relativistic, moving at significant fractions of the speed of light, and the degeneracy pressure increases less rapidly with density than needed to support the additional mass. Beyond the Chandrasekhar limit, no stable white dwarf can exist. The degeneracy pressure is insufficient to balance gravity, and the object must collapse further, either forming a neutron star if the collapse can be halted by neutron degeneracy pressure, or continuing to collapse into a black hole. A newly formed white dwarf emerges from the planetary nebula phase with a surface temperature of perhaps 100,000 degrees Celsius, making it one of the hottest objects in the galaxy and causing it to shine brilliantly in ultraviolet light. However, with no internal energy source, the white dwarf simply radiates this heat into space, gradually cooling over time. The cooling process is surprisingly slow, because the white dwarf's high density means it has an enormous heat capacity, storing vast amounts of thermal energy that must be radiated away. Initially, the cooling proceeds relatively rapidly by stellar standards, with the surface temperature dropping by half in perhaps the first 100 million years. As the white dwarf cools further, the rate of cooling decreases, and after several billion years, the white dwarf has cooled to temperatures comparable to the sun's surface, appearing yellow or red rather than white. The interior structure of a white dwarf is largely crystalline, at densities of 1 million grams per cubic centimeter and temperatures below about 10 million degrees. The carbon and oxygen nuclei, stripped of their electrons by the extreme conditions, arrange themselves into a lattice structure to minimize their mutual electrostatic energy. This creates a crystal, a solid body the size of Earth but made of carbon and oxygen nuclei embedded in a degenerate electron gas. The crystal structure was predicted theoretically in the 1960s and confirmed observationally in 2019 when astronomers detected the signature of crystallization in the cooling rates of white dwarfs. The realization that white dwarfs are giant cosmic diamonds, literally crystals of carbon and oxygen, captures the imagination even as it represents solid physics and observational confirmation. As white dwarfs cool below about 5,000 degrees, their surfaces begin to acquire thin atmospheres of hydrogen or helium, material that either remained from the progenitor star or was accreted from the interstellar medium. These atmospheres, despite being just a tiny fraction of the white dwarf's mass, dramatically affect the cooling rate by acting as insulating blankets that slow the escape of heat. Hydrogen atmospheres are particularly effective insulators, and white dwarfs with hydrogen atmospheres cool more slowly than those with helium atmospheres, leading to differences in observed temperatures and colors at given ages. Beneath the atmosphere lies a thin envelope of the same material extending to about 1% of the white dwarf's radius, and beneath that, the electron-degenerate interior extending to the core. White dwarfs can sometimes re-enter the realm of active phenomena if they exist in binary systems. When a white dwarf has a close companion star, it can accrete material from that companion if the companion fills its Roche lobe, the region within which material is gravitationally bound to it. Hydrogen gas from the companion spirals inward through an accretion disk, gradually settling onto the white dwarf's surface. This accreted hydrogen compresses and heats until it reaches the point where hydrogen fusion can ignite. However, unlike in a normal star where fusion is self-regulating, the degenerate matter beneath the accreted layer does not expand when heated, so when fusion begins, the temperature rises rapidly, the fusion rate accelerates exponentially, and a thermonuclear runaway occurs, producing a nova explosion. A nova is not the destruction of the star, but rather an explosion in the accreted material on the white dwarf's surface. The runaway fusion blasts the accumulated hydrogen into space at velocities of thousands of kilometers per second, brightening the system by factors of 10,000 to a million, enough to make a previously invisible star suddenly visible to the naked eye, hence the name nova, meaning new star, given by ancient astronomers who had no idea such objects were actually old stars undergoing explosive episodes. After the explosion, the white dwarf, essentially undamaged, continues accreting material from its companion, and after several decades to thousands of years, enough material accumulates for another nova eruption. Some systems called recurrent novae have been observed undergoing multiple nova outbursts, confirming this model of repeating thermonuclear explosions on white dwarf surfaces. If the white dwarf continues accreting material and its mass approaches the Chandrasekhar limit, something more dramatic occurs. As the mass increases, the white dwarf's interior density and temperature increase as well. If the white dwarf is composed primarily of carbon and oxygen, as most are, and if its central temperature reaches approximately 1 billion degrees while the mass is near the Chandrasekhar limit, carbon fusion can ignite in the degenerate core. Like the nova explosion, but far more violent, the fusion begins as a runaway in degenerate matter, and the entire white dwarf is consumed in a thermonuclear explosion that releases about 10 to the 44 joules of energy, equivalent to 1 or 2 times 10 to the 51 ergs, comparable to the total energy the sun will radiate over its entire 10 billion year life, but released in seconds. This is a Type Ia supernova, and unlike a nova, it completely destroys the white dwarf, leaving no remnant. Type Ia supernovae are remarkably uniform in their properties because they all involve white dwarfs near the Chandrasekhar limit undergoing thermonuclear explosions. This uniformity makes them valuable as standard candles for measuring cosmic distances, since their peak luminosity is approximately the same regardless of where they occur. By observing Type Ia supernovae in distant galaxies and comparing their apparent brightness to their known intrinsic luminosity, astronomers can calculate distances to those galaxies with good precision. These measurements played a crucial role in the 1998 discovery that the universe's expansion is accelerating, driven by dark energy, a finding that earned the Nobel Prize in Physics in 2011 and revolutionized our understanding of cosmic evolution. The ultimate fate of isolated white dwarfs is to cool indefinitely, eventually becoming black dwarfs, cold, dark objects no longer emitting significant radiation. However, the cooling time to reach this state is measured in trillions of years, far longer than the current age of the universe. No black dwarfs exist yet. Even the oldest white dwarfs, formed from the first generation of low-mass stars billions of years ago, still glow faintly, their surfaces at temperatures of several thousand degrees. In the distant future, when the universe is vastly older, white dwarfs will be the most common type of stellar remnant, with black dwarfs eventually dominating completely once cooling is complete. These objects will drift through galaxies long after star formation has ceased, monuments to stars that lived and died in an earlier, more active epoch of cosmic history. White dwarfs also play important roles in galactic chemical evolution. The material shed during the planetary nebula phase returns to the interstellar medium enriched in carbon, nitrogen, and oxygen synthesized during the star's evolution, particularly during helium burning and the AGB phase. This material mixes with pristine hydrogen and helium and becomes incorporated into the next generation of stars and planets. The type Ia supernovae produced by white dwarfs, accreting to the Chandrasekhar limit, are responsible for producing most of the iron group elements in the universe, including much of the iron, nickel, and cobalt found in planets and living organisms. Thus, white dwarfs, despite being stellar corpses, continue to influence galactic evolution through their contributions to the chemical enrichment of the interstellar medium. Chapter 11. Neutron stars, compact remnants. When massive stars explode as core collapse supernovae, they leave behind remnants even more exotic than white dwarfs. Neutron stars, objects so dense that protons and electrons are crushed together to form neutrons, creating matter at nuclear density compressed into spheres just 20 kilometers across. A neutron star contains more mass than the Sun packed into a volume comparable to a city, creating gravitational fields so intense that the escape velocity from the surface approaches half the speed of light. These objects represent matter in its most extreme accessible state, laboratories where nuclear physics, general relativity, and quantum mechanics all play crucial roles, and where conditions exist that cannot be replicated in any terrestrial experiment. The formation of a neutron star occurs during the core collapse of a massive star. When the iron core exceeds the Chandrasekhar limit, electron degeneracy pressure can no longer support it, and the core collapses catastrophically. During this collapse, lasting less than a second, the core density increases past nuclear density, about 400 trillion grams per cubic centimeter, the same density as an atomic nucleus. At these densities, the distinction between individual nuclei disappears, and the matter becomes a continuous fluid of neutrons with a smaller admixture of protons and electrons. The collapse is halted when neutron degeneracy pressure, analogous to electron degeneracy pressure but operating on neutrons, becomes strong enough to balance gravity. The core rebounds slightly from this supernuclear density, sending a shock wave outward that eventually blows apart the star's outer layers in a supernova explosion. The newly formed neutron star is incredibly hot, with temperatures exceeding 100 billion degrees immediately after formation. Most of the gravitational potential energy released during the collapse, about 10 to the 46 joules, goes into neutrinos that flood outward from the neutron star,